So this lesson on continuity is about using limits as a way of understanding different types of breaks in graphs. In general, as it says here, if a function is continuous, well, before even I talk about what it says here, just in general, a function is continuous if there's no breaks. For example, x squared is continuous. A linear function is continuous. There's no breaks in the graph at all. It's continuous for all real numbers. That said, a lot of functions are not continuous. For example, this weird mess of a function I see off to the right here. And I want to understand these ideas of discontinuity using limits. So it says a function is continuous at a point if the value of the function at that point is the same as the limit at that point. And we'll look at all these examples in a bit. A function is continuous at a left endpoint if the limit as we approach from the right is the same as the value of the function at that point, and the other way around for a right endpoint. So let's look at all these examples. So for example, this, if I just pick a point on this function, let's say right here, the function is continuous right there because the value of the function is the same as the limit at that point. Whereas if I look at this point right here, the function is not continuous right there because the value of the limit at that point, which does not exist, is not the same as the value of the function at that point, which is 0. And that means the function is not continuous in several places. There's several places this function is not continuous. And there's different types of discontinuity. And there's three types of discontinuity I want to talk about: removable, infinite, and jump. So a removable discontinuity you can also think of as a pointed discontinuity, which should sound familiar. And for something to be a removable discontinuity, the limit at that value, if we're looking at some point A, the limit should exist. And the function may be defined at that point. It doesn't have to be, but at this A, whatever this is, the function may be defined, it may not, but the limit should exist. However, the limit does not equal the value of the function at that point. As always, the best way of approaching these things is to look at it. So there are two removable discontinuities here. One is right here. I'll just kind of highlight all these in yellow. So if I look at that point there, when x equals 4, the limit does exist. If I ask you what is the limit of f of x, and maybe I'll label this y equals f of x. If I ask what's the limit of f of x as x approaches 4, that equals 0. If I ask you what is the value of f at 4, it equals -1. And so we call that a removable discontinuity. So right here we have a removable discontinuity. And it's clearly a break in the graph right there, and we call that type of break we call removable discontinuity. There's another removable discontinuity, but it's not right here. All right, so that's a little bit different. So another removable discontinuity is at the very end right here, this endpoint. That said, removable discontinuities and points of discontinuity are kind of the same thing. That's an infinite discontinuity is a vertical asymptote. And so this is a way of defining really what a vertical asymptote is using limits. And we've kind of seen this before. A vertical asymptote or an infinite discontinuity is where the limit as you approach from the left or the right is either infinity or negative infinity. So I think that's quite clear. Right here we have a infinite discontinuity. So at 4. So f of, at 4, function f has an infinite discontinuity. That's the only infinite discontinuity in this particular graph. Which leads me to this last one right here, which is a jump discontinuity. And for a jump discontinuity, it has to have these specifics, these characteristics. The limit from the left and from the right should both be defined, but they should not equal each other. And that's what we see right here. As you approach from the left, the limit equals 2. As you approach from the right, the limit equals 1. And so they're not the same. And notice how that's different from the removable discontinuity. As you approach, for example, if you look right here, so if you approach from the left and the right, you have the same value. And so that's a jump discontinuity, which is, literally the graph just kind of jumps. And so while I wouldn't ignore these definitions with limits, at first I would just focus on just getting a feeling for the visuals here. of these three types of discontinuities, and these aren't the only types, but these are the three types we'll look at. They're fairly, a jump is just literally a jump in the graph. A removable discontinuity is related to like a point of discontinuity, which you've seen before, and an infinite discontinuity is a vertical asymptote. So let's look at this function here. Okay, bit of a mess, that's okay. I have a function. First, let's determine where the function is continuous, and then I want to describe the 5 discontinuities. There's 5 discontinuities in here. But first, where is this function continuous? Well, it's first of all, the function starts at -5, but doesn't include -5. And then I have a number of breaks. Now, we don't want to mix up where it's continuous with the domain. I will say the domain of this function, and I'll write that down. The domain of this function is x is greater than -5, and x cannot equal, 3, and x does not equal 5. This is meant to go on forever. So that's the domain. The domain is everything greater than -5 except 3 and 5. However, in between there, it's not necessarily continuous in all those places. For example, at -1 right here, the function is defined. F at -1 is 4. The function is defined. But there's clearly this vertical asymptote or infinite discontinuity right there. So notice the function is defined, but there is a discontinuity. Same thing at 1. The function is defined at 1. 1 is in the domain, but there's a break there. There's a discontinuity there. So we don't want to mix up continuity, something being continuous, with having a domain that's defined there. That's it. Where is the function continuous? Well, in these sort of intervals. And so maybe I'll erase some of my highlighting here. And for example, it's continuous from here to here, from -5 to 1. It's continuous from here to here, just after -1 up to +1. It's continuous from here to here. It's continuous from here to here. It's continuous from here to here forever. It's continuous in 5 little sections, but not between them. And so this function is continuous. I'll use interval notation from -5 to -1, but not including -5 and -1. It's not continuous at those points. And then it's a union of that. It's continuous from -1 to +1, but not continuous at those points. And it's continuous from 1 to 3. And it's a union of, it's also continuous from 3 to 5, but not at 3 nor 5. And then it's also continuous from 5 all the way to infinity. So it goes on, and you never reach infinity. So I'm going to erase my domain now, just because that really wasn't what the question was asking. This is where my function is continuous. And maybe I will just highlight these little sections to make it more clear. I'll say one more thing about it once I've done my coloring. I mentioned endpoints at the beginning of the lesson. If this endpoint at -5 was filled in, then it would be we'd say it's continuous at -5, because that's an endpoint. So if the endpoint is filled in, we say at -5 the function is continuous. But it wasn't, so it's not. Whereas on the other way, it goes on forever. So now, what are the 5 discontinuities we see here? Well, there's 3 removable discontinuities. And where are they? There's a removable discontinuity at -5, there's a removable discontinuity at 1, and there's a removable discontinuity at 5. So there, and there. Those are our removable discontinuities. There's one infinite discontinuity, and that's that vertical asymptote. So that's at -1. That kind of stands out. And there's one jump discontinuity. And the jump discontinuity is only at 3. Right there. That's where the function jumps. Now, there's a decent chance you're watching this and you're wondering, why is this not a jump discontinuity? And again, notice the limit as we approach from the left and the right is the same. And that's why it's not a that's why it's not a jump discontinuity. Because if you look as we approach 1 from the left and we approach 1 from the right, the limit equals 0 from both the left and the right. So yes, that there is that point in a different spot, but that doesn't matter. The limits are the same as we approach from the left and the right. So it's a jump discontinuity if the limits are different as you approach from the left and the right. So lastly, I just want to kind of talk about a question which partially involves why we use the phrase removable discontinuity. And so if you have a removable discontinuity, the idea is it can be removed. So what does that mean? Well, I have 3 equations here, f, g, and h. They're all in piecewise form, and they're all discontinuous at some point. For example, f of x is currently discontinuous at 0, because if you look at the 2 pieces, 0 is not included. So right now, x at 0 is not defined, which means if it's not defined at 0, it can't be continuous there. For g of x, x at 1 is not defined currently. Now I have a blank right here, so maybe I'll erase that part. But if you look at the top piece, when x is 1, we're also dividing by 0, but function is not defined at 1. And if you look at the bottom piece, or bottom function, these 2 pieces, one's less than pi over 2, one's more than pi over 2, but neither includes pi over 2. So as it stands now, each has a blank third piece that I could potentially fill in. As it stands now, each of these functions is undefined at some point, 0, 1, and pi over 2. At least one of these discontinuities can be removed. It can be removed by filling in a point, but other ones it cannot be removed. So what does that mean? Well, let's look at function f. Okay, and for this we got to think about what's happening as we approach 0. I want to visualize what's happening to this function as we approach 0. And what that really means is I want to find the limit of the 2 pieces from the left and from the right. So first, for f of x, I want to find the limit as we approach 0 from the left. And if I look at my equation, as we approach from the left, that means we look at the top piece. And so I'm getting infinitely close to 0 from the left, so 2 minus 0, which equals 2. Oh, wrong color. OK, let's now see what happens as I approach 2 from the right. So I want the limit as x approaches 0 from the right of f of x. And so again, I'm now looking at values more than 0. So I'm looking at this piece right here. And that's x squared. So it's 0 squared, which is 0. So what does that tell me? That tells me as I approach from the left, the function is getting closer to 2. As I approach from the right, it's getting closer to 0. They're not the same. So that tells me actually this is a jump discontinuity. So I might as well label that down. There's a jump here. It's a jump discontinuity, which means I cannot be removed. There's nothing I can do to basically fill in this gap. And so it cannot be removed. Visually, I have from one side, I have this line. It looks like this. The other side, I have half a parabola. I can't, they're not at the same point. One's too higher than the other. I can't connect them. You may think, why can't I draw a vertical line? Well, if I draw a vertical line, it's no longer a function. At this point, at x equals 0, I have an infinite number of different points that come out. So there's no way I can just remove that discontinuity. So hence it's not a removable discontinuity. All right, again, I think with each example it should get a little bit clearer. Let's look at function g of x. 1 is the point that we want to pay attention to. So what's happening as I approach 1 from the left and the right? That was f of x. So, and by the way, before I go on, that means this piece here I'm just going to leave blank because there's nothing I can do at 0. I can't, like I said, I can't fill in that gap. I can't remove the discontinuity. So I'm just going to leave that blank right there. Or in fact, I'll just erase it now at this point. There. All right, let's look at g of x. OK, so g of x, let me just write down the equation for the one piece I'm really looking at, is 1 minus x squared over 1 minus x. And that's the entire function except at 1. So let's first simplify this a bit. I have a difference of squares in my numerator. And so I can simplify this down to 1 plus x. Now I could say it's 1 plus x, except where x equals 1. That's it. That's already kind of stated. If you look back at the restriction, we only look at that piece, 1 minus x squared over 1 minus x, if x doesn't equal 1. So it's not wrong to say x doesn't equal 1, but that's already been stated, really. So now that I have this simplified, let's see what happens as I approach 1 from the left, as I approach 1 from the right of g of x. Well, as I approach 1 from the left, there's nothing stopping me from just substituting with 1, and I get 1 plus 1 is 2. As I approach from the right, it's the same equation, 1 plus x. So 1 plus 1 equals 2. And so as I approach 1 from the left and the right, I have the same value, which means this is a removable discontinuity, which means I can remove the discontinuity. So what does that mean? I can see right now that the way this function is set up, as I approach from the left and the right, it's getting infinitely close to 2. But when x actually equals 1, the function is not defined. Because if I look at this piece, when x actually equals 1, I'm dividing by 0. So how can I remove the discontinuity? How can I fill in that gap? I can just add an extra piece where I say when x equals 1, just let this equal 2. So that little piece I just added, that second piece of the equation, now removes the discontinuity. If x is not 1, I look at the top piece. If x actually equals 1, I look at the bottom piece. And now there's no more gaps in my function. This function is now perfectly continuous. I removed that discontinuity that used to be there. I filled in the point of discontinuity. And you can only fill in these discontinuities if it's a removable discontinuity. And so g of x, that was a removable discontinuity, and not only that, I removed this discontinuity by creating that extra piece. So lastly, let's look at h of x. Oh, I didn't give myself much space here. Let's go off to the side. So for this, I have a separate piece for going from less than pi over 2 and more than pi over 2. So let's find the limit for h of x as I approach pi over 2 from the left, and as I approach pi over 2 from the right. So I approach from the left, I have 1 over, well, I'll just write down actually h of x first. So in this case, I will look at the top piece. So I have 1 over pi over 2 minus pi over 2. Well, that doesn't do me any good, because I get 1 divided by 0. So unlike before, I couldn't just substitute this in. So what do I have here? I have, I'll put an x here again. And I have x approaching pi over 2. So there's no way I can really simplify this. So I can just see now, as x approaches pi over 2 from the left, all of this right here is going to be a negative number. How do I know that? Because I'm approaching pi over 2 from the left. That means it's a little bit less than pi over 2. And again, unlike before, I couldn't just literally substitute x with pi over 2. So I have to imagine, okay, I'm not substituting x with pi over 2. I'm imagining I'm substituting x with numbers that are really, really close to pi over 2, infinitely close to pi over 2, but a little bit less. So a tiny bit less than pi over 2 minus pi over 2 exactly means the whole denominator will be really close to 0, but negative. And so if I go 1 divided by a number that's really close to 0, but negative, I get out more and more negative numbers. And so I can see the limit as I approach from the left must be negative infinity. So right off the bat, I can see this is not a removable discontinuity. There's no way it can be. But let me do the other side. The other side is just the tan of x. And so again, if I just try to substitute x with pi over 2, tan of pi over 2 is undefined. So that doesn't do me any good. But what does this equal? Well, at least it is just tan of x. And so let's think about what the tan of x looks like as x approaches pi over 2 from the right. So let me visualize the tangent function. Tangent function has an asymptote right at pi over 2 as well as at negative pi over 2. So here's my tangent function, and it repeats. Right here is pi over 2, though. So I want to think now what's happening as I approach pi over 2 from the right. Well, as I approach from the right, I can just see from visualizing this graph that it's getting infinitely negative. So the limit of h of x, the limit of tan of x, as I approach pi over 2 from the right, must be also negative infinity. So they're the same, but they're not numbers. Right? Infinity is not a number. So they are the same, but there's still not a removable discontinuity. This is an infinite discontinuity. And so which means no matter what, I can't remove the discontinuity. I can't fill in that gap. Really, if I were to graph this, it would look from one side, it would look something, it would go, have an asymptote like that, another side, an asymptote going down. There'd still be this vertical asymptote in the middle, but I can't just fill in that gap. Yes, they're getting infinitely close to one another, but they're also going down forever. And so again, it's not a removable discontinuity. Which means when I look back at this piecewise form, there is nothing I can put right here to fill in that gap. So I'm just going to erase the whole thing. So from these three piecewise defined functions, only g of x had the removable discontinuity. So not surprisingly, only g of x could be, could I actually remove the discontinuity? And I did that by putting that little 2, saying when x equals 1 exactly, the output is 2. All right, notice pretty abstract lesson at some points. Students tend to find continuity a bit difficult because quite often you have to visualize the behavior of functions that may be a bit complex. It's definitely easier if you are actually given a graph. All right, with that said, you're probably done.